These are the notes for AP Calculus on the topic of power series. So in previous sections on infinite series, we've looked at series where the terms of each series were constants. But now, the next few sections we're going to look at analyzing series whose terms actually have variables. They're not all just constants. So a famous one we can look at here is f of x equals e to the x. That can be represented by this power series where it's x to the 0 over 0 factorial, x to the first over first 1 factorial, and so on. So the way we could write that in sigma notation, it's an infinite series, we could write it starting from n equals, looks like the first thing we substitute in is 0. It goes on forever, so to infinity. And then the formula is not too hard to write for this one. It would be x to the n, so that might be x to the 0, then x to the first, then x to the second, over n factorial. So that's another way of writing this function e to the x. So each of the terms, notice, has an x in it. So in general, a series in the form, for it's an infinite series, a sub n here represents the formula that gives you each term, but that doesn't have the x in it. It's the constant part of it, in other words. And x minus c to the n, then it's called a power series, where it's centered at c. So whatever that c is there, that's what's centered. In other words, whatever x coordinate would make that 0. So in the one up here, we can see there doesn't appear to be a c. That's because c equals 0. So this one, this power series here is centered at x equals 0. So what we're interested in is the values of x for which the power series reaches a limit or converges and is not infinite. So there's three general ways a power series can converge: at a single point, an interval, or for all values of x. So what these would look like on the number line, there could be just some center here where the power series converges for that particular x value, but that's the only place it converges. So on either side of that, all x values less than that center, it diverges, and all x values greater than that center, it also diverges. So we've got a center C. The radius of convergence, since it doesn't go anywhere from the center on either side, the radius convergence here would just be 0. And the interval convergence, well, there is no interval here where it converges, so that does not exist, or there is none. The other possibility sometimes happens, there's an interval at which it converges. So you still have some center, which we'll call C. But if there's an interval, that means from that center, it's going to extend a radius, both directions, the same amount. That's what's called the radius of convergence. So there'll be some amount R that converges there on that interval. So the radius of convergence here would be R. And at the endpoints there, in this case, this would be C plus R. And this would be the center minus R. It's either going to converge or diverge right at the endpoints. So if it converges, then at that endpoint we can use a bracket, show it includes the endpoint. But if it doesn't converge at the endpoint, then we can use a parentheses to show it's not included. So it just depends on the problem. Sometimes at the endpoints it will converge, sometimes it won't. So, and then on either end, again, outside that interval, it diverges for all x values that are not in the interval. Okay, so the interval of convergence here, and the way I drew it here, in this case, if it's included, would be from C minus R to C plus R. And again, sometimes they're both parentheses, sometimes they're both brackets, and sometimes like this, one is the parentheses and one is the bracket. And then the other possible is you have some center here, but it converges for all values of x. So it converges everywhere and diverges nowhere. So it's basically the entire number line, both directions. So the center is C. The radius convergence would be infinity, because it goes on forever. And the interval convergence here would be from negative infinity to infinity, because it converges everywhere. So those are the three possible cases we can run into on these power series problems. Then, just to recall some of the tests we looked at that we'll be using today. The ratio test, remember, is one test that determines whether an infinite series converges or diverges. If the limit, what we'll be focusing on right here, is if the limit is less than 1, then it converges. That's when we're looking at where it's less than 1, that'll determine where it converges. If it's greater than 1, it diverges. And then we'll be using tests like the p-series test and alternate series test at the endpoints to determine if it converges at the endpoints. If they should be parentheses or brackets. Because when L equals 1, using the ratio test, the results are inconclusive. So it doesn't tell us whether it converges or diverges right when L, the limit is 1, and that's where the p-series and alternate series will help us out. Okay, so let's take a look at some examples here. So it says for each power series, find the center, the radius of convergence, and the interval of convergence. So we're going to use the ratio test. Which is the easiest way to start out first. And that's the limit as n approaches infinity of the absolute value of a sub n plus 1, if you look right back here, divided by a sub n, an absolute value of that. And that's equals some limit there. In this case, since we're going to want it to converge, we're going to make that less than 1. So a sub n plus 1 would be x to the n plus 1 over n factorial divided by a sub n, which is just x sub n over n factorial. Now let's go ahead and simplify what's inside there. So remember, dividing by a fraction is the same as multiplying by its reciprocal. So instead of divided by that, you can multiply by n factorial. Oops. Made a mistake there. Just realized I forgot to put n plus 1 here. I just put n accidentally. That should have been n plus 1 factorial. Again, we're still doing the limit as n approaches infinity of this. So let's see how this simplifies. Well, x to the n plus 1 and x to the n. Well, that's the exponent is 1 bigger than this one. So that's like having, if you had x to the 8th divided by x to the 7th. Well, if the exponent's 1 bigger, you're just going to cancel that out and be left with an x. So the same thing happens here. And so that we're just left with x. Or another way to think about it, you subtract the exponents. 8 minus 7 is 1. Here, n plus 1 minus n is 1. So we just have x left. And then with the factorials, this number is 1 bigger than this one. So let's say if we had 6 factorial over 7 factorial, where this number again is 1 bigger. Well, 6 factorial is 6, 5, 4, 3, 2, 1. We'll plug together. This is 7, 6, 5, 4, 3, 2, 1. We'll plug together. So you can see everything would cancel out, and we just left with 7 of the 1. So the same thing happens here. Those cancel out, and we're just left with n plus 1. That number down there, not factorial anymore. So what we have left here is x over n plus 1. absolute value. And then notice, since n is starting at 0, 0 plus 1, and 1 plus 1, and 2 plus 1, notice this n plus 1 will never be negative. So the absolute value will not affect that. The only thing it might affect is the x. So we can simplify this, and then let's put back our limit. Remember, this is the limit as n approaches infinity of this. So we'll have the absolute value of x over n plus 1. So then if we substitute in infinity for n, the absolute value of x divided by, well, infinity there, the 1 is negligible, so look for infinity. Well, absolute value of x over infinity, no matter what this is, it's going to be some number over this huge number, it's going to get closer to 0. So that's 0. So when is 0 less than 1? Well, it's always less than 1. So this is the case where it always converges. And again, the reason why we said it less than 1 because of the ratio test. We know this converges if the limit is less than 1, which in this case it always is. It's 0. So this is where you have the entire number line at converging for. So the center would just be 0. There's that x equals 0. Because you can see there's no nothing in there, plus or minus anything in the parentheses with x. And the radius of convergence would be infinity, because again, since this is less than 1, this always converges. And finally, the interval of convergence would be negative infinity. Okay, let's take a look at another example. So on this one again, let's use our ratio test. So the limit as n approaches infinity. The absolute value of a sub n plus 1, so we substitute n plus 1 wherever there's an n. So n plus 1 factorial, that's x plus 2 to the n plus 1, divided by a sub n as it is, so n factorial times x plus 2 to the n. Okay, so let's go ahead and simplify this in a similar fashion. We can see, okay, with the factorials, let's see, this is 1 bigger than that one, so those cancel out, just leaving you with n plus 1 there. And again, since n starts out as 0 plus 1, and 1 plus 1, that would never be negative. So that part we can pull out of our limit as just n plus 1. Sorry, out of the absolute values. And then x plus 2 to the n plus 1 divided by x plus 2 to the n. Again, you would subtract the exponents. N plus 1 minus n would just be 1, so you'd just be left with x plus 2. But that part the absolute value could affect, because x could be anything, so it could potentially be negative. So then if we substitute and find the limit as n approaches infinity, if we plug in infinity, again, the 1 is negligible. We'll get infinity times the absolute value of x plus 2. And in order for this to converge using the ratio test, remember this has to be less than 1. Well, if you have infinity times something, how can that be less than 1? Well, it can't be, unless the only thing that would make this less than 1 is if this absolute value of x plus 2, and that equals 0. Because infinity times 0 is still 0, so that would make it less than 1. And the only thing that's going to make that 0 is if x equals negative 2. Anything else it won't. So this is a case where our center here would be negative 2. It converges there, but nowhere else. Anything else, it's not going to be less than 1, so it diverges everywhere else. So this is just where it converges at one single point. In this case, -2. So we can say the center would be x equals -2. The radius of convergence would be 0, since it doesn't go either direction from the center. And the interval of convergence doesn't exist. Okay, let's take a look at another example. This one is x to the n over n to the 5th. So again, using the ratio test, the limit as n approaches infinity, absolute value of a sub n plus 1, so x to the n plus 1 over n plus 1 to the 5th. And again, we divide by a sub n, the 1 as it is. Remember, dividing, save ourselves a step here, dividing by x to the n over n plus n to the 5th is the same as multiplying by the reciprocal, which would be n to the 5th over x to the n. Let's see what we're left with this time. The limit as n approaches infinity. Let's start with the n's first. Well, here, we can't really cancel anything out with the n's, because it's n to the 5th and n plus 1 to the 5th, because this could just be, like, let's say n was 3. This would be 3 to the 5th, and this would be 3 plus 1, 4 to the 5th. So you can see nothing cancels. What we can do is, since they're both to the same exponent, we can write it as a single fraction like this. Make it a little easier to see. And then we took that outside the absolute value because n is n plus n and n plus 1 are always positive there, so the absolute value won't affect it. And then here again, x to the n plus 1 over x to the n, so this exponent's 1 bigger. So subtract them would just leave you with x to the first of it. So that's what's going to be still inside the absolute value. It could still affect that. So let's go ahead and find this limit here. So if we plug in infinity, well, the plus 1 of the negatives, we end up with infinity over infinity to the 5th. So that is x. That's just, infinity over infinity is just 1. So the 5th is just 1, so we just end up with the absolute value of x. And again, to make sure this converges, we want to set this less than 1. So this is a basic algebra problem at this point. To make sure this is less than 1, we would just write, well, that means the distance away from 0 is less than 1. So on the number line, it would look like this. It could be 1 either direction. So it'd have to be between -1 and 1. So the way you can write that as a compound inequality would be -1 is less than x, which is less than 1. In this case, that's already solved. So this is where it's less than 1. But what the ratio test won't tell us is, does it converge or not when it's equal to 1? In other words, at the endpoints here, 1 and -1 would make this equal to 1. So if we go back here, we can see that. So if L equals 1, the results are inconclusive using the ratio test. So that's where these other tests come in handy, although the T-series test and the alternate series test primarily. So let's go ahead and test the endpoints one at a time. So it doesn't really matter which one you start with. Let's say we start with 1. So you just go back to the original series here. And actually substitute in 1 for x. Because we're going to see if this should have be or equal to or not. It should be a parentheses or a bracket. So if we substitute in 1 for x, that'll be 1 to the 5th over n to the 5th. Well, 1 to the 5th is just 1. So we've got, in our formula there, 1 over n to the 5th. And you can see this fits the p-series test, where in this case, p is equal to 5. And since p is greater than 1, that tells us the series converges. And since it converges, we know it would include the 1 there, so we put the or equal to. Now let's look at the case where x is negative 1, the other endpoint, to see if it converges or not there. The negative 1, well, oops. I made a mistake on this one, sorry about that. I wrote the wrong number, I realized the other one. This was an n, not a 5, my mistake. But 1 to any exponent, no matter what it is still 1. Okay? And I accidentally put a 5 there, I was looking at the wrong thing, that should be an n. Sorry about that. So this is one where it's an alternate series test, because when you plug in 1, you can see it's an odd exponent, we'll make it negative. When you plug in 2, it's an even exponent, we'll make it positive, so it'll keep alternating back and forth between positive and negative. So here's where we use the alternating series test. Forgot to write this one by P series. That's what we use it. So use the alternate series test. First you have to make sure the limit of this part, it doesn't include the negative 1 to the n, equals 0. So you see that'd be 1 over infinity to the 5th. So that is 0, first of all. If it's not, then it doesn't converge. And then you have to make sure each time you plug in the next number, the terms are going to get smaller and smaller. So if you look back at the alternating series test, right here, let's see if the limit is a sub approaches n approaches infinity, if a sub n equals 0, we tested that, that is 0. And what this part is saying on the alternating series test, that the term a sub n plus 1 is always less than the term before a sub n for all n. So the terms just keep getting smaller and smaller in magnitude. So you can think about if that would be true. So if you plug in 1, you get 1, right? If you plug in 2, it'd be 1 over 2 to the 5th, 3, 1 over 3 to the 5th, 4 to the 5th, you can see the terms are going to get smaller and smaller. So because of that, this also converges. But this time it's by alternating series test. So because of that, we would add an or equal to there. So in this case, both endpoints it converges at. So when we write down our final answer, we can see the center on this one will be right in the middle of those, so it would be x equals 0. Let's see, there's nothing with the x there. The radius of convergence, let's see, from the center it goes 1 each direction, so the radius of convergence would be 1. And the interval of convergence is both endpoints that are included, both of them are brackets, so it'd be from -1 to 1. Those would be the exponents that would cause this power series to converge. And let's take a look at some more examples here. Yeah, let's start with a ratio test. So the limit as n approaches infinity, absolute value of a sub n plus 1, so 2 to the n plus 1, exponent is 3 to the n plus 1, over 5n plus 1 to the 6th. And again, dividing by a sub n is the same as multiplying by its reciprocal. So that's multiplied by the reciprocal, so 5n to the 6th over 2n exponent is 3 to the n. So let's go ahead and simplify this. You can see when we're reducing this, the 5's. 5 divided by 5 is just 1, so those reduce out. And then the n's aren't going to be negative, and we have n to the 6 over n plus 1 to the 6. So we can pull that out. So we have the limit. N approaches infinity. Again, they're raised to the same exponent, so that's the same as n over n plus 1 to the 6th. But in this one, we also have 2 to the n plus 1 and 2 to the n. So you can see, well, cancel out if you subtract the exponents and just leave you with a 2 on the numerator, which also is not affected by the opposite value because it's positive. And then we'd also have x minus 3 to the n plus 1 and x minus 3 to the n. So the similar thing happens there. Let's cancel out, just leaving you with 1x minus 3 on the numerator. But that is what could be affected by the opposite value because the x minus 3 could be negative. And again, if we plug in infinity there, so for n, we'll end up with infinity over infinity to the 6, so that's just 1 to the 6, which is 1. So all that's left, that is 2 times the opposite value of x minus 3. And again, using the ratio test, in order for this to converge, this has to be less than 1. So this one just takes a little more work than solving for x. Again, it's just an algebra problem now. So you first isolate the absolute value. So you'd have to divide by 2 first. Take the absolute value of x minus 3 less than 1/2. And then you can rewrite it. The distance away from 0 would have to be 1/2 of this x minus 3. So you put it in between there. So negative 1/2 is less than x minus 3, which is less than 1/2. See how you write it as a compound inequality. Then you just add 3 to all those. You get the x by itself in the middle. And adding 3 is the same as adding 6 over 2, so that would be 5 over 2 is less than x, which is less than 6 over 2 plus 1 over 2 is 7 over 2. So there's our interval, but again, we have to figure out at 7 over 2 and 5 over 2, should those be parentheses or brackets? Do those converge at those points or not? So let's go back to our original, substitute those in. One at a time. So we'll have substitute in for x. So if we plug in 7 over 2, well, that's 7 over 2 minus 3, which is 6 over 2, is going to be 1/2. So if we simplify this, 2 to the n, notice these are both to the n, so that would be the same as 2 times 1/2 to the n. So those would cancel out, just giving you 1 to the n, over 5n to the 6th. And again, 1 to any exponent is just 1. You can see you can just pull out the 1/5 as a constant, and again we have a p-series one. In this case, p equals 6, which again is greater than 1. So this one converges by the p-series test. So it's 7 over 2. Well, yeah, it should have 4 equal to it. And then let's try 5 over 2, see what happens when we substitute that in for x. See if it converges or not. So we'll have 2 to the n. Now 5 over 2 minus 3 is 5 over 2 minus 6 over 2 is negative 1 over 2. So this time when you multiply those together, 2 times negative 1/2, since they're both raised to the n, would be negative 1 to the n over 5n to the 6th. So again, since it's got that negative 1 to the n, this is going to be an alternating series. So again, if we just find the limit as n approaches infinity of the 1 over 5n to the 6th, you can see that would be 1 over 5 infinity to the 6th, which would be 0. That's the first test. And then just to make sure the terms would keep getting smaller and smaller, you plug in 1. you get 1 over 5, you plug in 2, plug in 3, you can see the denominator gets bigger and bigger, making it smaller and smaller. So this one also converges when x is 5 over 2, apply the alternating series test. So we'll also add the or equal to right there. Now we can put it all together in our final answer. So the center on this one will be x equals, you can see the middle of this, the way you can always get the center is average these two. 5 over 2 plus 7 over 2 is 12 over 2, which is 6. 6 divided by 2 is 3. Or you can look right here and see that. Remember, as x, whatever makes a 0 with the x part is going to be where your center is. It would be 3. And then your radius of convergence would be, well, from 3, you can see, or 6 over 2 goes a half each direction, right? See, whatever it's related, the radius convergence comes from when it's isolated, absolute value is isolated, what that number is. So there's 1/2 each direction from the center. And then your interval of convergence would be bracket 5 halves and 7 halves, both of them included. We've got it both endpoints of convergence. Okay, let's look at the next example. Okay, so again, using the ratio test, the limit as n approaches infinity, absolute value of a sub n plus 1, so negative 1 to the n plus 1 times x to the n plus 1 divided by 3 to the n plus 1. And then when you plug in n plus 1 here, plus 1, that's going to make it n plus 2. And then instead of dividing by this, that's the same as multiplying by the reciprocal. So the reciprocal would be 3 to the n plus 1 over negative 1 to the n x to the n. That's the limit as n approaches infinity. And let's see what we can simplify here. So let's start with the negative 1s. Well, negative 1 to the n plus 1, negative 1 to the n. That's just going to be a negative 1. But you can see the absolute value would make that a positive, so that basically goes away. And then 3 to the n and 3 to the n plus 1. See that x1 is 1 bigger on the denominator, so it's going to do with a 3 on the denominator. That. And then we have n plus 1 over n plus 2. See, those are not going to get affected by the absolute value at all. These are always what's going to be positive, starting at n equals 0. And then all that's left here is x to the n plus 1 over x to the n. Let's see, subtract the x one, so we'll just leave it with an x there. But that one could be affected by the absolute value. So again, notice when you plug in infinity on this one, the 1 and the 2 are negligible. Infinity over infinity, that's just going to be a 1. So all we're left with really is the 1/3 times the absolute value of x, and again, to converge, this using the ratio test, this has to be less than 1. So now to solve that, first isolate the absolute value, multiply both sides by 3. So you do the absolute value of x plus the 3. So that would mean negative 3 less than x, which is less than 3. So there's our interval, but again, we need to know, since the ratio test doesn't tell us when it's equal to 1, at 3 and negative 3, does it converge or diverge? So let's go back to the original series. Let's substitute in 3 first. So if we substitute in 3 for x, that'll be 1 to the n, 3 to the n, over 3 to the n, and plus 1. All right, well, you can see the 3 to the n's reduced out, those are just 1. And then we just have an alternating series test after that. You can see the limit as n approaches infinity of 1 over n plus 1 is 1 over infinity, which would be 0. And if you keep plugging in numbers 0, then 1, then 2, then 3, you can see the number keeps getting bigger, making the whole thing smaller. So this one converges by alternating series test. So you would put the or equal to there. Now let's take a look at negative 3. So if we substitute negative 3 for x back in the original power series here, that'd be negative 1 to the n, negative 3 to the n over 3 to the n and plus 1. So on this one, if you combine these, negative 3 times negative 1 to the n, that's just 3 to the n. Over 3 to the n plus 1. So those cancel out. All we're left with is 1 over n plus 1. So on this one, it's very similar to the power p series, except for that plus 1. So here we can actually use, well, I didn't put on the notes, but it's called the limit comparison test, where if you can find one that's very similar to this, that you know whether it converges or diverges, in this case, it was just 1 over n. Call that b sub n, this one a sub n. Well, you know by the p series test, p in this case is 1, that's not greater than 1. So this one diverges by the p series test. And to compare it, all we have to do is find the limit as n approaches infinity of a sub n, 1 over n plus 1, divided by 1 over n. And as long as this is a positive number that's not infinite, then we know it does the same thing as that one. So it would be 1 over n plus 1 times n. Let's see, when you plug in infinity into that, you just get infinity over infinity, which is 1. So since that's greater than 0, then this one also diverges. Does the same thing. That's our limit comparison test. Since it diverges, that means we don't put anything, we don't put the or equal to this up. So this one, we can say the center would be x equals, again, 0, right in the middle there. The radius convergence. I can see it from 0, it goes 3 each direction, so that'd be 3. Again, it's whatever that number is once you've isolated the opposite eye there. And interval convergence would be negative 3 with parentheses to 3 with a bracket. Because here it converges at 3 but not at negative 3. All right, let's take a look at one more example. Right. And using the ratio test, the limit n approaches infinity. Absolute value 2x minus 3 n plus 1 over 4. And when you plug in n plus 1 there, you end up with 2n plus 2 when you distribute out the 2. And then divided by a sub n, Same as multiplying by the reciprocal again. We'll do 4 to the 2n over 2x minus 3 to the n. Let's go ahead and simplify this. Let's start with the 4's. So 4 to the 2n and 4 to the 2n plus 2. Remember, you just subtract the exponents here. So if you go 2n plus 2 minus 2n, so you're left with 2, or 4 squared, which is just 16. So 1/16. And then here on the 2x minus 3 to the n's, this is what next one more. Those cancel out, just leave you with 2x minus 3. And that's what the absolute value could affect. In this case, there's no n left. The n's are gone. So in order to substitute an infinity in, so we just start with this, and this has to be less than 1. So if you multiply by 16, yeah, so I have 2x minus 3 less than 16, and then rewrite it. Negative 16 less than 2x minus 3 less than 16. Adding 3 to all three parts of the compound inequality gives you negative 13 less than 2x less than 19. Divide by 2 gives you negative 13 over 2 is less than x, which is less than 19 over 2. So there's our interval of convergence, except we still need to figure out at the endpoints if it converges or diverges. So let's start with 19 over 2. Okay, so 19 over 2 for x times 2 makes it just 19. Minus 3 is 16. So you can see, you can write 16 is the same as 4 squared. So those reduce out, and we just end up with 1. Well, it's an infinite series of 1, that means when you plug in 0, you get 1. When you plug in 1, you get 1. So you just keep getting 1. It looks like basically the infinite series looks like this. 1 plus 1 plus 1 plus 1 plus 1. So would that converge or diverge? Well, it just keeps getting bigger forever, right? Close to infinity, so that definitely diverges. So you don't put the equal to sign there. Now let's try negative 13 over 2. So if we put in negative 13 over 2 for x, again the 2's cancel, you get negative 13 minus 13. Gives you negative 16. And over 4 to the 2. Now this one we can split up, negative 16 into negative 1 to the n, times 16 to the n. And again, 16 to the n is the same as 4 to the 2n. So those are the same reduced out. You're just left with negative 1 to the n. So let's think about what would happen here. It is alternating series, but the limit doesn't approach 0. So that's one way to see it diverges. Or notice if you just plug in numbers, you plug in 0, you get 1. You plug in 1, you get negative 1. You plug in 2, you get 1. You plug in 3, you get negative 1. So you can see we keep adding these up forever. It's not going to converge because you get 1. Then you get 0. Then back to 1. Then 0. So 1, 0, 1, 0, 1. It just alternates back and forth between 1 and 0. It doesn't converge on anything. So that's one way to see it diverges. Or you can see by an alternating series test, all that's left of the formula is just 1. So that equals 1, not 0. That's another way to see it diverges. So they both diverge, so you don't put the equal to on either one. So on this one, the center would be x equals 0. It's not 0, my bad. The center would be what makes this 0. So you can see there's a couple ways you can do this. You can average the endpoints of your interval. So 19 over 2 plus negative 13 over 2 is 6 over 2, which is 3. half of 3 is 3 over 2. Or another way to see it, it's really whatever makes this term with x, it's raised to the n 0. So if you plug in 3 over 2, you can see the 2's cancel. 3 minus 3 gives you 0. That's another way to figure it out. Then the radius of convergence, well, how far is it from 3 over 2 to 19 over 2 and to negative 13 over 2? You can see that's 16 over 2 away, which is 8. So you can see on each direction it goes 8 away from there. So the radius of convergence would be 8. So it looked like it would be 16 if you look right here, but because that 2 gets divided by 2, it means 8 instead. And then the interval of convergence would be parentheses on both of them this time because it diverges at both of them. Negative 13 over 2 to 19 over 2. And that concludes the notes on the topic of power series.